Kia ora. I just got a copy of the 2021 probability distributions paper, so I'm going to go through it. I haven't had a look at it yet, so I kind of want to show you how I problem solve them as well. I might even have to skip some questions, who knows. Okay, so let's get straight into it. So, question 1. It is estimated that on Memorial Avenue in Christchurch there is probability of 0.45 of being required to stop encountering an amber or red light. I don't know if that's necessarily true. At each of the 6 sets of traffic lights on the road. It looks like binomial. Distances between each set of traffic lights range from 0.6 kilometers at the shortest to 1.2 kilometers at the longest. Interesting. So these traffic lights, 6 sets of traffic lights, and then each one of them is a 0.45, but the distances between them are different. Okay, I don't know what distribution this is going to be now. Suppose the number of times the driver is required to stop at least at the 6 sets of traffic lights when they drive completely. Oh, well, there you go. It is binomial. Justify the use of the binomial distribution to model the number of times a driver is required to stop when they drive the complete length of Memorial Avenue. Okay, so justify the use of binomial distribution. I do a bit of a fist for that. So it means fixed number of trials. They are independent. S, they have the same probability. And T, there are 2 outcomes. So I'm assuming we only probably need 2 things to get this. Probably a merit question, not sure though. Might be combined with the next one. Okay, fixed number of trials. There are 6 sets of lights on Memorial Ave. Mem Ave. I should probably say so the number of trials is fixed, but I know they get the point. Independent events. Each set of lights are not affected by others. If you were saying not, if you weren't justifying, if you were going against it, you could probably argue that independence is not actually true. But I'm just going to do each one. Same probability. It says, by definition, there is a probability of 0.5. P equals 0.45 for each light, each set of lights. And 2 outcomes, stop or not stop. Okay, normally you should probably put this into the sentence, but I'm sure these arrows make it fine. Calculate an estimate for the probability that the driver is not required to stop at any of the 6 sets of lights, or is required to stop at all 6 sets of lights when driving the complete length of Memorial Avenue. So it looks like Px equals... What are we going to say is success here? What did they say? Okay, so I'm going to say stop equals success, because that's what they gave us for the probability, because then P is 0.45, N is 6. So we want to know if they have 0 successes plus if they have 6 successes. So this means that they stop 0 times, so that's actually the stop 0 times, yeah, this one here, and then stop 6 times is over here. So what I'll do is I'm just going to go into stat, distribution, binomial. We're looking at a point, and we're looking at x equals 0 first, and we're doing it out of 6 lights, probability 0.45. So this is 0.0277. Oh, I guess I'm going 4dp today. Yep. By the way, I can totally make errors during this. I am just doing it off the cuff. Oof, I don't like these. 0.008. Let's see if I did it right. Wait. 1, 2, 3. Yes, I really want to make sure that I'm doing this right. Okay, cool. I'm going to add that up the safe way because I'm sitting an exam. Ooh, nice number. Yep, looks good to me. Yep, I'm fine with that. Okay, let's move on. For any given intersection with traffic lights on them, I don't know where the heck do we use this? Like, where is this piece of information going to be relevant? I hope that they make it relevant. Okay, for any given intersection with traffic lights on Memorial Avenue, proposed safety changes will increase the probability of being required to stop from 0.45 to 0.6. The driver can be considered unlucky in this new situation if they are required to stop at more than half of the 6 sets of traffic lights when they drive the complete length of Memorial Avenue. I mean, sure. That's what they said, so I'm just going to go with what they're doing. So it's now, P has changed to being 0.6, and we want to know the probability. Unlucky. So unlucky are the people that on the 6 sets of lights, right, there are 6 sets of lights, so they can either stop 0 times, 1 time, 2 times, 3 times, 4 times, 5 times, 6 times, right? The driver can be, if they're required to stop at more than half of the 6 sets, if they're required to stop, so I'm going to say this is stop at more than half. So these are the unlucky people. So it's P X is greater than or equal to 4. So that is 1 minus P is, and it's this white area, X is less than or equal to 3. Okay, so we go to here again. Distribution binomial. We're looking at a cumulative because we're looking at less than or equal to 3. We're going to find this white area, minus it off 1, that'll tell us this area here. All that's changed is our P value and our X value. Okay. So it's 1 minus 0.4557. That is 0.5443. I just want to double check that. More than half of the 6 at more than half. Ooh! Like I read that. At more than half. My bad. More than half, because half would be 3. Yes. Wait, if they stop at 3, yeah. Okay, cool, good. I didn't need to double check it. A person drives the entire length of Memorial Avenue to work and back home over a working week, Monday to Friday inclusive. Investigate. Oh shucks. Are we seriously not going to use these distances? Wacky. This is weird. This is a big throw because they're giving you numbers, so you're going to go and highlight them, and I don't know if we're even going to use them. Okay. Investigate the claim that this person will not experience an increased likelihood of being unlucky on every trip they take along Memorial Avenue during their work week. What? Will not experience an increased likelihood. Okay, I'm thoroughly confused. A person drives the entire length of Memorial Avenue to work and back after a working week. So they do 10 trips. Alright? They do 10 trips of the 6 lights. Investigate the claim that this person will not experience an increased likelihood of being unlucky on every trip. What? Okay, we've been given this information here, which I think is useless. I also think that this seems like it's useless information. I don't know. Okay, investigate the claim that this person will not experience an increased likelihood of being unlucky on every trip. See how this every trip makes me think we're not worried about the fact that there's 10 trips during their working week if the proposed safety changes are put in place. P equals 0.45 is less than 0.6. So P1, the first probability, that's what I'm thinking here. This number, this is the amount of times, this is proportional to the amount of times you stop. So when the amount of times you stop increases, of course it's going to take you longer. So I don't get the question at all. Investigate being unlucky. What the heck? So I'm going to go Px greater than or equal to 4 with P1 equals 0.45. I don't know. I think they want me to do a calculation like this. I don't know. I feel like I've been thrown twice. 1 minus 0.744. Was I going 40p or was I? Equals 0.2553. Would you look at that? The probability they want likelihood of being unlucky before the proposed changes were put in place was 0.2553, and that is which is less than after, when P x being greater than or equal to 4 with P2 being equal to, what is it? 0. Up here. 0. Oopsie, it's 5. 5443. I don't know how they want me to answer that. I think it's wrong. Because I've got this information, I didn't even use it. Investigate the claim that this person will not experience an increased likelihood. Claim is false. The claim is false and convoluted. I don't even know how to spell that. Convoluted. Sure. Moving on. Okay, a recent New Zealand study asked drivers to respond anonymously about their mobile phone habits whilst driving. 16.7% of people admitted to using their mobile phone while stopped at a traffic light. The Canterbury researcher was interested to see if the behaviour of drivers on Memorial Avenue was similar to the drivers in this New Zealand study. In September 2021, data was collected from groups of 10 drivers stopped at traffic lights on Memorial Avenue. What? So they went and asked the people while they were stopped at traffic lights. It's like way more dangerous than people texting while driving. Anyway, the number of drivers out of 10 who were using... Oh, right, they took photos or something. Okay. Who were using their mobile phones while stopped at traffic lights was recorded. The results are shown in the graph below. The experimental distribution shown in grey. These results are compared to the binomial distribution model. The theoretical distribution shown in black. Okay. First of all, doing this sort of data collection using a binomial distribution for this is interesting. I don't know why you wouldn't just find an average rather than doing it in groups of 10. What are we gaining from that? Anyway, the graph below shows the observed... Did I read this out? I think I read this out. The graph below shows the observed distribution graph as in a binomial distribution with p equal to 0.167. The theoretical model distribution shown in black. Complete the graph. Okay. I'm happy to do that. X equals 0. It's 10 drivers. The probability they gave us here is 0.167. So 0. I'm going to do them down here. X equals 0 equals 0.1609. And then I'm going to do 1. Oh, that's horrible quality for you guys, but x equals 1 equals, whoa, that's half the data pretty much. 3, 4. X equals 2, and that's all I need. What am I doing wrong? Oh, I'm doing CD, blimmin' numpty. Okay, P, point distribution, point. Notice that you sort of try and actively think about how, oh, dang it, I'm such a numpty. Hey, at least you know I'm doing this live. 0.3225, and then we'll look at 2. Guys, if you're ever doing maths, just learn how to make your zeros look like 2's. I can make a flippin' 2 look so similar to a 4. 2909. That's a lot. Even that makes me wonder, because that's 0.85. That's like only 15% of the data is missing. Seems a little odd. I'm just going to do a quick double check that I've done that. So there's the 15%. Wait, so that's 60. Oh, 75. 25% of the data is missing. My bad. Oh yeah. Yep. Looks about right. Yes. Okay, what do we want me to do? They want me to complete it. So I'm looking for 0.16. I like to do it like this. So this is 0.15. So 0.16 is going to be like there, right? They want me to do 0.32. So it's going to be around about here. And then they want me to do 0.29. So it's going to be around about here. Sweet. Oh yeah, that's a nice shape. Beautiful. I actually kind of want to, let's really complete this graph. That's what they wanted from me. That was a trick question there, guys. No, they won't get you extra marks by showing the remaining values. They could play you there pretty hard. Gotta be safe, gotta cover myself. So let's put in 7. And I'm hoping to see a like E negative 08 or negative 04. Yeah, so they're all very low, but I think you might have to draw them in. Okay. Discuss 2 features of the observed and theoretical distributions that justify the suitability of this binomial distribution model for the number of drivers out of 10 observed using their mobile phone. Okay, so we probably want to find some values. Whenever you justify these, the marking sheet will normally say something about like putting a value in there. So they want to know justify. So we see how it says justify. We're giving positives. We're going to try and give positives. We're justifying it. So I want to start off with. So I'm going to use fixed, independent. I'm just going to put them up to remind me. Same prob and 2 outcomes. Oh no, they want features from the distribution, my bad. So you don't actually need to do these. They want features from here. So I want to do things. Okay, I'm going to start off with these values here actually. I'm going to go, what percentage of data is above? So if I go like, let's say we go up to 6, so I'm going to go binomial, I'm going to go up to 6. So I want to know what happens with 6 or less. See how 99% of the data, so look at this, P, X is less than or equal to, I did 6, right? Yeah, less than or equals 6 equals 0.9997 from our model, from the model. That means that the data points 7, 8, 9, 10 will be very small. This matches, what's the word they use? Do they say observed? The amount of observed using mobile phones. Brackets out of 10. Will that be a good feature? I don't know. I really don't know. Okay, maybe we can do something like this. N times P. So I'm going to go 10 times 0.167 equals, so this is going to be our mean. How do you write that? I'm just going to write mean. I forgot what I kind of want to write mu, but I also don't want to write mu. Equals 1.67. Now, so now, and we can see, so according to our model, so we've used that data to our model to find the mean, right? So you can see that. I should probably show you how I'm doing this on the formula sheet. Okay, so see how you've got, here's binomial, here we are. So see how we've got, oh yeah, they do like mu. Mu equals NP. So we've got a model, so we can use that to find the mean of our model is 1.67. We can compare that with the highest peaks, which is not necessarily on our observed data. So this is actually, the highest peaks is actually mode. This is talking about modes. I should probably change how I'm doing that. So I just want to show you that, like, see how these are the clear, like, most occurring, and we can see that if you were to, we could actually go and work out an actual mean. Yeah, I should have done, this is I'm sort of talking about mode, so I'm going to change it. I'm going to just find what these values are around about and find a mean. Let's just do that. I'm going to go say that this is 0.125 times 0 plus, I'm going to say that that's 0.29 times 1, and then I'm going to say that that is 0.325 times 2, and then I'm going to say that that is 1.7, and then I'm going to say that that is 0.65. I'm going to say that that is 0.18. I don't know how, like, I'm getting more accurate as I go. And I don't know what happens at 6. What did I do wrong there? I typed something wrong. That times that. That times that. That times that. Plus that times that. Divided by 10. No, that's wrong. What the heck? What am I doing wrong here? Oh, there we are. Is that from 0.65? 0.02. And that's 0.2 as well. Shucks, that's a big error to make. Okay, so that's our mean. Actually, we want to compare. That's mode. Compared to an approximate mean from our observed data. And then you should probably type in, like, write out this calculation. So I'm just going to quickly, or as quickly as I can, do that. Times 0, nice. 0.29 times 1 plus 0.325 times 2 plus 0.2 times 3 plus 0.07 times 4 plus 0.02 times 5 equals 1.92. 1.92 is close enough to 1.67. Let's give them being only 0.25 bigger. So I'm comparing means. So what I've done is I've gone for my two features. I've compared like a bunch of data here and said that it's really similar. And then I'm also comparing the means of the two. I hope that's good enough. I'm just going to move on. Okay, so next we've got a beautiful colour picture. Oh, thank you for including Auckland in the thing. Wilding pine trees are a serious threat to the natural landscapes of New Zealand. Amen. Wilding pine is one that is grown from a seed that was not deliberately planted. I would say standard pines are a flipping threat. And grows in place where it was not wanted. Research has shown that on Rangitoto Island, the average number of wilding pines per hectare is 1.8. Okay. Use a suitable probability. Okay, yeah, I probably should have told you how I got that. Whenever you've got a rate, this is just a rate. See how it's a rate and it's a fairly low number? Now I can just jump straight to that's Poisson. Use a suitable probability distribution to calculate an estimate for the probability that there are more than 4 wilding pines in any hectare on Rangitoto Island. More than 4. So this is P, x is greater than 4, which is equal to 1 minus P, that x is less than or equal to 4. So go over to stat, distribution, we're looking at Poisson, we're looking at cumulative, x, 4, mu, 1.8. Okay, so it's going to be 1 minus 0.9636 equals 0.0364. Conservationists consider it a success when the probability of finding at least one wilding pine in a hectare is 1/3. Okay. Calculate the model parameter that provides this result. They just sneak an excellence question in 2A2. Oh, love it. Okay, cool. So they said P x, finding at least 1, greater than equal to 1 equals 1/3. This is what we have. What do we need for this one? The parameter, so we know it's Poisson at this stage. I kind of want to fold my formula sheet, but that's a bit mean. So we've got this formula here that we're using. See how we've got a P x equals, and that's for finding a point on Poisson. So we want to find the parameter. There is only one parameter, so we're trying to find out what lambda is going to be equal to find this. So interestingly, probability x is greater than or equal to 1 is very conveniently so that 1 minus p x greater than equal to 1 actually finds us the probability that x equals 0. That's all that's left, because this is if there's 1 tree, 2 trees, 4 trees, 5 trees, right up. So this is all that's left over. So we now know that px is equal to 0 is equal to 1/3, or 1 minus 1/3, so is 2/3. So that's all we need. So now we've got a px equals, and it has to be 0 to get this, and I'll show you why. A few facts you need to know. 0 factorial equals 1, and anything to the power of 0 equals 1. That's all you need to know for this. So so this is the statement I'm going to put below the lambda one. So lambda to the power, and the little x is 0, e to the negative lambda over little x, which is 0 factorial, is equal to 2/3. Okay, now look at this. Lambda to the power of 0 is 1. 0 factorial, 1. So e to the negative lambda equals 2/3. Because it's just 1 times that divided by 1. So that's all that's left. Okay, how do you get rid of that? You just do the natural log. So negative lambda equals the natural log of 2/3, and so lambda is equal to the negative natural log of 0.666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666. So we go negative ln, and I'm going to put 2/3. So lambda would have to be 0.4055. Let's just double check this. Calculate the model parameter that provides this result. Yeah, so that would mean lambda would have to be 0.4, and I mean right now it's 1.8. So conservationists are not considering this a great success. Okay, Rangitoto has an area of 2,311 hectares. 100 hectares make up an area of 1 square kilometre. Convenient. Provide 2 reasons why it may not be appropriate to use a Poisson model for the number of wilding pines on Rangitoto Island in any square kilometre. Nice. I like it. These may not be appropriate ones. They're way more fun because you get to be critical, right? In the modern era, humans love to be critical. So I remember Poisson. Oh shucks. Proportional occurs rarely. Independent, and then there's independent. This is 2 S's together, so that's simultaneous. Simultaneous occurs never. These ones go together. Okay, whoopsies. In your exam, please keep this blank, but I can do what I want. Okay, proportional. So we're going to go with, what ones don't work here? So we've got, well, I mean, if they're talking about Rangitoto, we've got like a island like this, got some volcano-y thing here. And you get a big advantage for knowing a little bit about Auckland. Right, so you've got a volcano bit, and there's like forest stuff that grows up around here. But then there'll be like grassy places, places where the toilets are built. You got stony places. Oopsies, I wasn't even. That's a crap picture. It looked cool when I was drawing it. Okay, reason 1. Independent. Ooh, I like that one. I'm gonna go with that. Independent. Okay. Wilding. So sometimes, pretty much, normally they'll give you the information here. Wilding pine is one that is grown from a seed that was not deliberately planted. Wilding pines come from pinecone seeds. Oh, actually, that may not even be true. I'm assuming they have pine cones. Come from pinecone seeds, which have multiple seeds in a bunch. This means Actually, you could argue simultaneous occurs never, and you could also argue independent. I'm going independent. That if if there is a wilding pine in a hectare, there will probably be others. So that means independence is out. They are therefore not independent. This is how you guys write, so I'm going to try it like that. Okay, reason 2. Simultaneous occurs never. I think that's actually fine. Occurs rarely. I could argue this, but the fact that it's 1.8 is actually pretty rare. I'm gonna go with another. I'm gonna go with probably some proportional argument. I want to argue proportional. There will be. I don't actually know. There will be areas on Rangitoto that have different probabilities. For example, on rocky places there will be less wilding pines, and fertile ground will have higher rates. I don't even know if I used any of these things here, but I guess it's in any square. Yeah, this is this any square kilometre. I think that one sort of argues that there are square kilometres that will be better than others. Okay, let's move on. Over many years of trying to eliminate wilding pines from New Zealand, it is known that in cleared areas there is a probability of them returning. For the North Island, data suggests this is likely to occur anywhere between 3 and 18 months after the land was cleared. For the South Island, it is likely to be anywhere between 3 and 27 months, with the most likely time at 12 months after the land was cleared. Ooh. If writing was... Dang, is one rectangular? Look at this. So we've got a minimum and a maximum. This one you've got a minimum and a maximum, and you've got this 12. So my question is, does this mode only go with the South Island? Oh yeah. This is likely to go anywhere between after it was cleared. I'm going to say that the north is a rectangle and that the south is triangular. So we're going to need the numbers. I'm going to go from 0. Let's see how many we got here. 5. No, surely that. I'm just going straight for it. I'm sure it fits. 5, 10, 15, 20, 25. I want to go up to 30. 0. Okay, so we need to find heights first. We actually get given heights. I think, yeah, you get heights for, look at this, rectangular height, here we go. 1 over b minus a. 1 over 18 minus 3. 1 over 18 minus 3. And then our other height is going to be 2 over b minus a. 2 over 27 minus 3. So that's going to be our two heights. I'm going to draw a triangle here and a rectangle here. I wonder if that marks on everyone's exam. I wonder if it helps. We'll find out. Okay. 1 over 18 minus 3. So 1 over 15. I kind of want. What I'm gonna do is I'm gonna leave the decimal there, and then move on. And then move the next one 2 over 27 minus 3. That's 1 over 12. And I'll get a decimal of that. Oof! This is pretty ugly. I'm going to make this 0.083. I'm going to go with 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, I'm happy with that. 0.09. So then this is going to be 1, 2, 3, 4, 5, 6. This is 0.06. And then this is 0.08, 0.07. Okay. Then we can get nice heights. Okay, so let's do our rectangular first. Our rectangular goes from 3 to 18, and the height of the rectangular is 0.067. Starts at 3. 0.067. I'm going to go here, and it goes across to 18, right? So here. So let's draw that. And then we've got to draw our triangular. So that goes from 3 to 27, which is here. And it peaks out at 0.083 over 12. So over 12, I'll put that in there, 12, 0.083. Like here. Some people bring rulers. Others have a steady hand. Oh dang it, now I've said it, there's no way I'm going to get this one. Okay. Oh! Yeah, dang it, that's mediocre at best. That'll do, donkey, that'll do. Just to really complete these, I want a pretty base for them. I gotta admit, kind of pleasing to look at. If wilding pines re-establish themselves within 8 months of an area being cleared, it is expensive to clear the area again. So this is also important. 8. Let me just double. So this is south, this is north. Okay. Calculate an estimate for the probability that a randomly selected area in the North Highland and a random selected area in the South Highland both see a re-emergence of wilding pines before 8 months after. Before 8 months after clearing. Right. So we're going to work out this area. And we're going to work out this area, and then we're going to multiply them together. That's what it looks like to me. Yep, that's fine. So with a rectangle, you just go the base times the height. So the base is what? 5 times, and what was the height? 1 over 15. Okay, that's P. I'm going to use an N at the North Island. I should really use an X. I don't know why I did that. Oh well. Less than 8 equals that. Equals 1 over 3. And then we want to know PS less than 8. So we've got a base, so it's going to be, so we need to work out a height. We should really start by working out the height. So it's here. Oh, do you know the best part is, if my diagram is legit, like I actually don't have to do a calculation. I hope that's right. So it's what? This is 0.05. So this is going to be 0.045. We're banking on it. Let's get a formula. So we're going to use this formula here because it's between, so there's A and there's C. So it's between A and C. So we're going to use that. What information do I need? I'm going to put it like this. I can't put it all on the screen for you guys. Well, maybe I can. There. Yeah, that's going to have to do. And sideways, why not? Okay, so we're going to go on the top, we're going to do a big bracket. 2, and the point of x is 8. 8 minus a is 3. So this is all my top stuff, so I'm going to close off that bracket, start a fraction, open another big bracket, then do the bracket at the bottom. Then we're going to do b minus a. So b, I've got to double check. A, B, C. Yep, cool. B minus a, so we went up to 27 minus a is 3. Multiply that by c minus a, so that was at 12 minus 3. That looks good. 5 over 108, 0.046. That's why you don't trust your diagrams, people. But at least I can see that it's close enough. I could have made an error there. This whole thing could have errors. So find an area. Oh, do I need to show my working? I actually don't know if I need to show my working. 2, 8 minus 3 over f. What are we doing? 27 minus 3, 12 minus 3 equals 5 over 108. What a glorious 5. Okay, so the area of that triangular bit is going to be half times base. Base is the same at 5. 8 minus 3, 5. Times 5 over 108. And that is 25 over 216. Is that a nice number? Yep. No. Yeah, by the way, this could be laden with mistakes, and if you guys really care that much about the answers, you can double check them, but I think my working should be fine. Okay, so calculate and estimate that a randomly selected area in the North Island and both see a re-emergence of wilding pines before that. So we're just going to do is 1 over 3 times 25 over 216, and that is 25 over 645 plus 3. Looks good to me. Okay, cool. What do I reckon that is? It'll be a merit, and then you combine it with this, probably making an excellence. No, that can't be right, because you're already getting the excellence from here. Maybe there's 2 excellence questions. Calculate the probability in at least one assumption to be made, whether this assumption is likely to be valid. This is a classic. It's always independence. Independence. That what happens with pine reemergence in the north doesn't affect pine reemergence. Now, do I have to say this in the south? Or it's an or vice versa. Now, explain whether this assumption is likely or not to be valid. This is probably valid as the companies are independent. Given they are that far away, I'm going to say different islands. Although the weather patterns will have similarities, and the species of pine being used in the same year, I don't know, at similar times will likely be related, and that will affect that will mean that they won't be independent. I don't know. I don't have enough room. I think I said it verbally anyway. Let's move on. Two different computer operating systems, System A and System W, are very popular. Apple Windows. Thanks, guys. The table below shows the probability distributions of a random variable E. Here, E, what's that going to be? E. Ethernet. I don't know. The number of extras, such as speakers or wireless keyboards, an owner of System A and an owner of System W buys for their computer over the time they own it. Ew. Okay. The expected values for the number of extras for System A and System W are very similar, but the standard deviation for System W is much larger than System A. See the values below. Incredible! Use statistical reasoning to explain what features of the distributions cause these similarities and differences in expected values and standard deviations for the number of extras purchased. Okay. Okay, I can see here. All right. This value, the distribution of this, it looks like it's like inverted. Like it's going down and then it goes back up again, right? So this is what W looks like. I'm gonna put W down here. And then the other one, see how you got like peaks in the middle around about 3 or 4? So that one is like, probably looks a little bit more like this. I'm just going to do it like that just to make it clear what I'm talking about. And that's System A. Right? So the reason being, standard deviation puts, as soon as you get a large number with a large value, you because you're squaring, this is going to make the model know. That's pretty much how standard deviation works. Spread outedness. Standard deviation is how spread out something goes. So when there's lots of values on either side, these get conflated so that they make the standard deviation way larger for System W. Whereas here, most of your data points are centralized, so you've got less spread, right? It's looking a little bit closer to being bell-shaped, whereas this one's like bimodal for some reason, with a lot of data around the large values and then a lot of data around the smallest value. But then we've got to fit in 2.5 lines, 3.5 lines. Can't even count. Yeah, use statistical reasoning to explain what features. Reasons for similar expected values. Okay, I think I can do standard deviations. I've got to think about this one a little bit better. Oh, the mean is calculated by adding all values and dividing by the amount, thus finding a center value. Because It's actually, do you know what the best part is? This is sort of not really how we even do. It's a frequency table, so I'm not even given the right definition for how mean's calculated here. Yeah, it's a summation times the summation of what times the probability. Because system W has a high probability for x equals 0, it brings down E of E similar to system A, which has a traditional normal distribution with the center being. Oh man, that's a crap explanation. Oh, I'll lose a mark there. I don't have enough space. Reason I like this one's a way cooler question anyway. Come on. So standard deviation is more affected by extreme values because of this. How to explain that? The squaring component. Thus, system W's extreme values having high probabilities makes the standard deviation of E for W significantly larger. Significantly larger for then system system A. Cool. Alright, you can tell I'm getting sick of this question already. Did I get this? Did I get this? Reasons for similar expected values. Yeah, I think this is, because the system has high probability for it brings down. What I didn't mention here was the fact that pretty much that because this value here is high and these values at the end are high, it centralizes to find an expected value in the middle. And I think that's kind of it. I don't know. I sort of screwed you guys. Whereas this one here, it's very clear why the mean value is the center. So I don't know. I don't have space. Move on. Okay. Compare the probabilities of buying 5 or more extras for system A and system W. Px is greater than or equal to 5. Ooh. Alright, we can just do calculations. System A, P is greater than or equal to 5. 0.08 plus 0.04 plus 0.02. And then we'll do system W, 0.18 plus 0.14 plus 0.15. So bring that over. Compare the probabilities. The prob of system W's users buying 5 or more is way higher than system A users. What a comparison! Okay, for both system types, it is believed that the time taken for a serious system error to occur from purchase can be modeled by a normal distribution with a mean of 5.5 years. Oh man, my one chance to normal distribution, I do it crap as. Mean equals 5.5, standard deviation 0.9. Estimate the probability that given a computer from either system lasts for more than 6 years until its first serious error. It will last more. Ooh, conditional. Okay. So they want to know 6. And they also, given that 6 happens, so this becomes our sample space, and then they want us to go over to 7.5. So they want to know the crisscross out of the cross. Oh yeah, I like it. I don't mind a bit of conditional. Okay, so my lower value, first of all, I'm going to do this. Oh, I was already 99999. Alright, so Px is greater than 6 equals 0.2893. Px is greater than 7.5 is 0.0131. So all we need to do for this conditional is 0.0131. It's this area here divided by this area that it is within, 2893. 0.0131 divided by 0.2893. 0.0453. So, estimate the probability that a given computer from either system lasts for more than 6 years until its first serious error. If, where does it say if? That given computer lasts for it will. Oh yeah, no, that's good. Good grammar. Nice. Oh yeah, cool question. I like it. Another operating system, System L, Linux, is known to experience a serious system error within the first 2.5 years after purchase, or more than 8.5 years after purchase, with total probability just over 4.4%. What the heck? Oh yeah, let me redeem myself. Oh, that line's kind of cool. Okay. 2.5, 2.5, or more than 8.5. The total probability of just, oh, what the heck? Just over 4.4%. So that means this is 2%, this is 2%. Unless I've read the question wrong. I don't like that just over 4%. Justify whether the normal distribution, ooh, I like this, I'm going to do it like this. Greater than 2%, greater than 2%. Can be used to model the time to serious error. Ooh, okay. So pretty much we're doing a two-tailed distribution. Are we? Yeah, let's do it that way. You could do it two ways. You could do like a inverse. No, you couldn't, because that would have two unknowns. No. Okay, so our lower becomes 2.5, our upper becomes 8.5, and it's the same standard deviation. Okay, so not necessarily true. So P that x is between these two numbers. If mu equals 5.5 and standard deviation equals 0.9, this is what we typed in, equals 0.9991. Now, this means that so this is what did I just work out? That's this probability. Right, so we found this probability here, and that is not equal to 0.96, which is 1 minus 0.04, alright? So I think that's the calculation. Yeah, using the model from Systems Apple and W, Px less than 2.5 plus Px greater than 8.5 equals 0.0009, which is not 0.04. It's that those two areas there. It's not 4%. It's way off. Justify. You can't use this model. Okay, moving on. Last question. Okay, C. Another company developed an operating system named System C. Chrome. This is fun. You guys are probably having fun in this exam talking about what operating system is it. The company is fairly sure that they have developed System C so that the time for a serious system error to occur is longer on average than the other operating systems, A, W, and L. For System C, the time for a serious system error to occur is on average 6.25 years, with a standard deviation of 0.8 years. Details of a sample of that many computers sent to the company. Distribution of so many systems. Justify the use of normal distribution with a mean of 6.25 years and a standard deviation of 0.8 years to model the time to serious error after purchase from a System C. Okay, my brain's getting foggy. How long have we been doing this for? Hour and 8. Okay, I don't know why. I mean, we've got this. From the large sample taken, the sample statistics for X bar and S match very closely to the model mu and sigma. That's just a way of saying that this mean, right, so this X bar here and this standard deviation here. So pretty much they chucked it into NZ or Insight or whatever you use, and they put this data in, and this is the mean and standard deviation just from doing from modeling it on this program. And these values are so close to 6.25, like 6.236 and 0.8. They're so close that that's a really good reason to do it. Also, I've mentioned that it's a large sample, so to model the same. Okay, now it says justify. I really want to talk about this. This is dangerous as heck. Why the heck is there at 6 point whatever years this worrying mode value? Strange mode But because I've said justify, I can't really talk about that mode. So what they do want us to do is name, N-A-M-E. So name, I've forgotten what I do for normal distribution. So this is asymptotic, which means it goes to it can go positive, negative, infinity, which doesn't really work here, to be honest. Oh shucks, it's been too long. This is that the mean equals mode equals med, which is this is a good one. We can use that for justification. Oh man, N. What do I use? I don't think I use name. Why am I doing name? Did someone else show me this? My one's got a B in it because it's bell shaped. Well, anyway, I'm just going to go from the dome. It's bell shaped. What else can I see here? There's not actually many. There doesn't really seem to be. Yeah, it's really nicely bell shaped. Except I want to mention that mode for a mode at 6.9. That there, I do kind of want to mention. See how I've managed to sneak it into the justify one. Let's make that into a comment. Why not? What else do I want to say? There's no skew. It is a very good model. If only that data was snipped in here, it'd be beautiful. Yeah, mean and mode, central and equal to each other. What else? Do they need some calculations? Use statistical reasoning calculations. How am I going to use calculations? Okay, what I'm going to do is I'm going to use standard deviation. They want me to do a calculation. So 3 times sigma equals 3 times 0.8 equals 2.4. Right? Now, so therefore 6.25 plus 2.4, 6.25 minus 2.4. Just because they need calculations, they ask for it, so I'm going to do some. .65 equals I need to do it again. 3.85. Now 8.65 would be around about here, and 3.85 is around about here. Yeah, look at that. 99% of data lies within 3 standard deviations either side. That's my calculation. Beautiful. I'm going to stop there because I think I've gone for too long. I want to clarify that this is not necessarily correct. I just wanted to give a video for you guys just to see that you might have, just to double check over the exam, to show people that haven't seen the exam. Yeah, I would say overall nice exam. This is cool. I like it. Every question's got nice little twists. It's not the same as every other year. Nice diagram. I like this. Yeah, cool context. Only problem I had really was that dodgy. This is weird. I find that a little bit weird that they would give you that information, and I don't really understand this question, so I might have got this question wrong. I think it's a little bit of a throw here, but overall, nice paper. That's been the 2021 probability distributions paper. See you.